S over root 2, sine S over root 2, and S over root 2, while S belongs to this interval, as you can see. The topic is simple steps compared to what we had previously in other courses. It's very, very simple. Now, for the unit tangent vector, let's see the regular curve on R. If you want to have your unit vector tangent, all I have to do is to get R dash at this point divided by the magnitude of the R dash vector. That's going to be the tangent at this point. Remember that when we try to get the equation of the tangent, we usually have R, we get R dash, which is the vector of this tangent. But if you need to put this vector into a unit, all I have to do is to divide by the magnitude, and it's really very simple. That's an explanation of R of t, which projects the points that will form the curve that you are dealing with. If you need to find the tangent at this point, what I have to do is to get R dash at this point. That's going to be the vector of t. If you need to have it as a unit vector, you divide by its node. And of course, R, if it was R of S, so t at this node is equal to R dash at this node, and the magnitude will equal to 1. For the principal unit normal vector, which is a perpendicular vector on the tangent, the principal unit normal is a unit vector that points in the direction of the change of the tangent vector as you move along the curve. It is defined as t dash, so once you have the tangent vector, differentiate it, and then by the magnitude of t. If we are dealing with R, it means get the second derivative of R by the magnitude of the second derivative of R, or the acceleration in general. So, if the parameter of the vector function is the arc length, all I have to use is R double dash of S node by R double dash of S node magnitude. Properties to the tangent vector, the normal vector that we are talking about is always orthogonal on the tangent vector, points toward the concavity of the curve. It shows the direction in which the curve is turning. Number 3, used in curvature calculations. Magnitude t dash is the curvature k of your curve. For curves in the plan, the vector n2 is called the unitary or the interior normal, corresponds to the vector n of t. These are some clarification of this curve, and that's the tangent line, and that's the direction of the norm or the principal unit vector that we will need. Now to find the principal, for an example, for a unit vector of the principal unit vector on a unit circle, it's really very simple. I have the R now. The R is going to be simply cosine t, sine t. That's the general parametric shape or parametric representation of a general circle. If you are talking about a unit circle, so R, which is the radius, is going to equal to 1. So I will have R of t equal to 1 cosine t sine t. Getting the tangent direction for this, or the tangent vector for this R, is going to be simply just differentiating with respect to t. So it's going to be negative sine t and cosine t, as you can see. That's a negative sine t and that's a cosine t. The second steps of taking the derivative of t in order to get the direction of the normal. So I will differentiate this guy once more, which means it's the second derivative of R. This is the second derivative. So differentiating this once more, it's going to be negative cosine t plus negative over sine t. Now I have t dash. I will get the magnitude of this vector, of the t dash, which is simply square root of cosine square t plus sine square t. This is what we get now as a magnitude. So taking the first component, cosine square, then the second one, which is sine square, putting them together under the square root, which is going to come up to 1. So the principal unit normal vector now at the time being is t dash over t. I will start to divide these values over this one, which is 1, which will leave you with negative cosine t and negative sine t. That's it. Now, almost going toward the center of the circle. I will need to solve some problems from this is sheet 4. I'm sorry, it's my mistake here. This is sheet 4, not sheet 3, that we are dealing with, because this the 3 is already done. We solved all its problems in the previous videos. Also, we handled a couple of problems in the previous sessions. I will tell you problem number 4 was handled in the previous session. For this one, I will need to solve with you problem number 5 and problem number 6. Hopefully, we will be able to do this in this session, inshallah. So, I will start find the parametric representation of the given curve and the tangent line to the curve. Now we need to find the tangent of this curve. From the first log to this curve, I have, as you can see here, a cylinder, which is x squared over 4 to y squared equal 1. That's a cross section, which is an ellipse, and that's with the z equal to 2, planned at z equal to 2, at the point root 2, 1 over 2, and 2. So all I have to do now is to try to get the r component, and then r dash, and then the equation of the tangent, and then making substitution to determine the value of t, and so on. But the problem that will arise now is simply that we need to parameterize this equation. So in order to start with this is the equation of an ellipse. So I will use the parametrization. That's x equal to a cosine t and y equal to b sine t, which is the parametrization of an ellipse on this form. Of course, for my ellipse, you will find that a squared equal 4 and b squared equal half. Remember this. So a squared equal 4, which leads to a equal 2. B squared will equal to 1 over 2. So b by itself is going to be 1 over root 2, as you can see. I have a and b, cosine theta. So simply, the parametric representation is x is going to equal to 2 cosine t, y is going to be equal to b sine t. And the z will leave it as it is, which is 2, because it doesn't contain any variable, so it will remain the same. Now I can write the r component, which is going to be 2 cosine t in the direction of I, 1 root 2 sine t in the direction of j, and the 2 in the direction of k. Here we go. To get the equation of the tangent, I will need the vector, and then after getting the direction of the vector, I will need the point. The point is given, which is root 2, half and 2. So all I have to do now is to get r dash, and the r dash will be negative 2 sine t. I will differentiate this guy, it's going to be a cosine over t. This is going to be a 0, I left it for you, in order to know that the third component is equal to 0. The problem is, I need to find the values of this guy. In order to find the values of this one, or for r dash, I will need to identify t. How to get t to substitute here and get this direction from r? How? By equating or getting a relation at the point root 2, half and 2. So all I have to do now is to take 2 cosine t equal to root 2. So I will have cosine theta equal root 2 over 2. And sine theta 1 over root 2, which leaves me with theta equal pi over 4, like the previous example. So this is going to be negative 2 over root 2, and this is going to be a root half, actually. So substituting, as I told you, by 45, which is pi over 4, will leave you with root 2.5 and 2. Now, the equation of the tangent is really very simple. All I have to do is to write the equation of this tangent, is to write the point lambda times this vector. Okay? So this is r dash, these are the values, as you can see, negative root 2.5 and 0. This is the point, and that's the point, I'm sorry, and that's the vector. So now the line equation is going to be the point plus lambda times the vector. All I have to do is to make direct substitution, as you can see. Here is the point, which came from r, and that's the r dash vector coming from our vector. Okay, Shabab? Tamam. Perfect. Also, I have another problem, which is 5b, and here instead, he's giving you z equal to x squared plus y squared over 4, and he's not giving you z as a value, he's giving as a number, he's giving you z equal to 4 of x. Now I will have to think clearly about what I'm going to do. And unfortunately, here you will have to try to find the best parametric representation for your equation. Now I can see that I have an ellipse, which is x squared, y squared over 4, and z equal to 4 of x. So all I have to do is to use x, which equal to the main form of an ellipse. We already did that previously. So this is actually the main function. And before going further, okay, as you can see, that's an paraboloid. I'm sorry, that's a paraboloid, and that's a plane. So the intersection between them, it will give you an ellipse. I need to see what's the case or what's the equation of this ellipse in order to start parametrizing. So all I have to do first is to make these two guys equal to each other in order to get the intersection between this paraboloid, elliptic paraboloid, and this plane z equal to 4 of x. So now I will just replace z by 4 of x. So the equation at the time being will be, as you can see, 4 of x equal x squared plus y squared over 4. There is a lot of ideas about parametrizing. I will use the elliptic or the ellipse here by forming an ellipse equation from these guys. There were another ideas. I will push you, or I will show you how to go through it shortly, but let's first finish this idea. Now I made the substitution as I told you. This is the equation that we are talking about, x squared plus y squared over 4 equal 4 of x. I will move 4x from the right hand side to the left hand side. So it's gonna be x squared plus y squared over 4 plus equal 4 of x. I will move the 4 of x to the other side. Now I can get a complete square for this guy. Remark that I have x squared minus 4 of x, and this is plus y squared over 4 equal to 0. Now I will start making a completing square. Plus y squared over 4 equal to 0. From here, I will try to open just a small bracket, taking from x squared just on the x, dividing this value on 2, which is gonna be negative 2. So the first square is x squared. First, second times 2 is gonna be negative 4 of x. The last square, which is gonna be a positive over 4. So I will need to omit this value. This is why I will put negative 4, and that will leave me with x minus 2 to the power of 2 plus y squared over 4 equal to positive 4. I will divide this equation on 4. That will leave me with x minus 2 to the power of 2 divided by 4 plus y squared divided by 16 equal 1, which is an equation of an ellipse in the general form, where alpha, or the coordinates of the center of this ellipse, it's gonna be 2 and 0, where a for the semi x in the x direction, it's gonna be 2, and the semi x in the y direction is gonna be 4. And your parametrization now can be put on this form. For the x component, it's gonna equal to 2, which is the x component in the center, plus an a times cosine t. So it's gonna be 2 cosine of a t if you are using the t standard for this parametrization. And the 4y is gonna equal to, still same way like, it's gonna be the b, which is a 4 of a sine t. Okay, what about the z? Now I have x and y. So these two guys' problem are solved. But z equal 4 of x, which means that the z component will be a 4 times 2 plus 2 of a cosine t. That's the parametrization that I'm going to use with this curve. Okay, now, as I told you once more, this is to making the completing square. This is going to be the equation of the ellipse that I told you about. So, in order to parameterize it, I will have x, which equal to the component in x by a cosine t. And for y, it's going to be the components equal to 0 because I don't have any displacement in the y direction. But it's going to be a 4 for the semi-axis in the y direction, which is going to be 4 sine t. And the z equal 4 of x. So that's the 4, that's the value of x. This is x, y, and z. Now back again to the main line, to the main equations, nothing new for us. So I will start at the point which is 4, 0, and 16, but stop. 4, 0, and 16, these are related to Cartesian coordinates. I will need to find the corresponding values for 4, 0, and 16, but with relative to the t value. So how to do this? I will try to solve these equations. So the first component should equal to 4, the second component should equal to 0, the third component should equal to 16. So simply, if I have 4 of a sine t equals 0, that will leave me with sine t equal to 0, that's t equal to 0. So I'm suspecting that the result, in order to get my point, I will, this point which is 4, 0, and 16, in the t coordinates, t should equal to 0. Let's check that. Cosine 0 is going to equal to 1, so the sum of them is equal to 4. We are in a very good condition. Sine 0 equal to 0, so y is going to be 4 times 0, which is more than perfect. For the third component, it's going to be cosine t, which is cosine of a 0, 1. So it's going to be 2 plus 2, which is 4. 4 times 4, it's going to be a 16. So it's a het. That's the value of t. Now I have the value of t. I have r with me. I can get r dash simply by differentiating r. So it's going to be negative 2 sine t. It's going to be 4 cosine t. And it's going to be a negative of an 8 sine t. That's r dash. Now substituting the t by the 0, I will get the vector. Now I can write the equation of the line. That's the point. And once you start substituting by t equal to 0, this is going to be 0. This is going to be 1. This is going to be 0. So this is the main equation of this tangent line. Before finishing this lecture, I want to show you if I made another substitution and what may happen. So it's the exact same problem, and I will try to handle it exactly in the same manner, but I will try to make just a small change in the value of t. So I'm sorry, in parametrizing, and this is major. Actually, I could skip this slide, but I wanted to show it in front of you that if I went to a parametrization direction and it didn't work, start to readjust your parametrization. So exactly in a similar manner, I will start with, this is the second equation, represents a plane and a paraboloid. So their intersection is going to give me an ellipse. So instead of going through the ellipse equation, I'll start thinking about putting the x equal to t, and this way I will have z equal to 4 of t. If I make these substitutions here, so now I will replace hx by t, so this is going to be t, this is going to be 4t, and I will get the value of y. Here we go. This is actually 4t, that's t squared, y squared over 4. The only missing variable is y. So I start to solving for y this equation. And y squared over 4 equals 4t minus t squared. And this is how y squared is going to be 16t minus 4t squared. Taking a square root for both sides. So y is equal to positive or negative the square of 16t minus 4t squared. Now I have a parametrization. The parametric representation in this case is going to be x equal to t, y equal to positive or negative the square root of 16t minus 4t squared. z equal to 4 of t. This is actually x, y, and z as functions in t, in the variable t. Now I will try to get my r, but before going through it, I have a condition here for r, that 16t minus 4t squared must be greater than or equal to 0, and this will leave me with this result, that t should be greater than or equal to 0 and less than or equal to 4. That's the interval of definition of t till the time being. All work nicely. We don't have any problems whatsoever. Okay, the problems will arise right now. Getting the r, which is going to be t, we leave this for the time being. Most of our negative square root 16t minus 4t squared and 4t of a. The problem will start once you start to get the value of t. You will end up having t equal to 4. And once you start getting the r dash, that's the problem. Once you differentiate this guy, it's going to be 1 over 2 the root of 16t minus 4t squared and times 16 minus 8t. All of this, I have no problem with it. Once you start substituting with t equal to 4, this component will be undefined. And in this manner, if I use this parametrization, I'm going to stop because it's not going to work. So I will have to reconsider my parametrization strategy from the beginning once more and start to make it happen once more, as I told you. This is why I wrote this comment earlier this morning. As you can see here, although all the steps are correct, all of them, and we have our velocity vector and everything, but when we solve by t equal to 4, the result will be undefined in the j direction. So this is why we will have to change our assumption in the parametrization sequence. Well, actually, this is why the previous solution did work. Okay, so I started with considering x equal to t, and I start working with my steps. I actually faced the problem that one of the components is not defined. So I start to rethink once more about this intersection, which is going to give me an ellipse, trying to put it on the normal form, trying to use the parametrization relative to the ellipse or the elliptical shapes, make it possible for me to get the equation of the tangent in a perfect manner. There is another problem, so this is why this solution, this one, is not going to work, as I told you, because it's undefined at the final step. I will leave problem number 6 to the next lecture. I will go through it. It needs you to go through it in depth, but as we have short time here, we are running out of time, and because we are going through the break, I hope you enjoy, inshallah, with the feast and everything. I will continue after the feast break. Please take the advantage of this week and study from the start. It's all related to each other, all depend on each other. So please try to review your lectures. It's really very important. Once more, for the 1000th time, don't study mathematics by reading or trying to follow up. Things make smooth in front of you, but once you start writing with your hand, a lot of problems will arise. So please use a pen and start writing. Thank you very much. Appreciate it. I hope you the best in all times, and Ramadan Mubarak and happy feast on all of you. Thank you very much. Thank you. Bye.